Hello everyone, welcome to a new video. Today we are going to be looking at the force-directed layout technique that is used to place objects equidistantly in space. The objects are typically connected in some way, so we can think of them as nodes in a graph. In this simulation, I'm using commonly occurring chemical compounds to illustrate the power of this technique. In this particular example, you see the benzene molecule, where there are 6 carbon atoms at the center and the 6 hydrogen atoms linked to each of the carbon atoms, and it's a planar structure. And as the algorithm converges, we seem to be getting the structure of the actual molecule. Let's look at the two main forces that we consider in the force-directed layout. Given two nodes that are connected by a spring of length d and a spring rest length of L and masses m1 and m2, the spring force is given by this expression here. C1 is a constant times the two masses times the logarithm of d divided by L. As you can see, the quantity log d by L is positive when d is greater than L and negative when d is less than L, which means that when d is greater than L, we have an attractive force which pull the objects towards each other. And when d is less than L, there is a repulsive force which pushes away the objects from each other. For every pair of nodes, regardless of whether they're connected to each other or not, which are at a distance d, we have the repulsive force, which is given by the following expression. There's another constant C2 times the two masses times a temperature parameter, which starts off at an initial value and progressively decreases so that the algorithm converges, divided by the minimum of the comfortable distance between the two objects and the current distance squared. Now all that's needed to do is to calculate the final displacement. All the forces that are acting on a node are summed up. They are multiplied by another constant, C3, and divided by the total mass of the object. All of this consists of one iteration of the algorithm, and this has to be repeated for several iterations with progressively lower temperature. Let's shortly look at the code for the force-directed repositioning function for our graph. This one takes a temperature as input, and we have defined the three constants as I described before. N is the number of nodes in our graph. We also initialize the forces array that's going to hold all the forces that will be acting on each node. We initialize it to 0 for every node, and then for each node we try to calculate the force acting on it on every other node. First we have the displacement vector, which is pointing towards node I. And then we have the length of our displacement, the direction of our displacement, and the rest length between node I and node j. Then we see if there is a connection that exists between I and j. we calculate the spring force as described and apply the spring force in the respective directions to both the nodes. Otherwise, we apply a repulsive force for every pair of nodes and then also add it to both the nodes. And finally, for every node, we calculate the displacement and translate the node's position by the given displacement. And that's it. If you like the video, please subscribe to the channel, and as always, thanks for watching.